week. I'm Meg Coffey. I'm the president of AWA+D, the Association for Women in Architecture and Design. And I'm especially pleased to see so many new names here tonight. So if you're not familiar with our organization, we are an organization for women, but not of only women. So all of you men that I see here tonight, you are more than welcome to join us. We have great activities, great events. So if you're not already a member of our awesome organization, please join us. And you can find out everything you want to know about us at our website, which is awa+d.org. As Christine is presenting tonight, if you all have any questions, please enter them in the chat and we'll have time for Q&A after the talk. So Christine is joining us today from Dallas, and that's one of the silver linings about these Zoom calls is that we're able to bring in experts from all over the world. And so we are just super pleased to have you here, Christine, and we are looking forward to hearing your talk.
Well, thank you so much. I'm so glad to be here. I'm glad to be doing this. It is a silver lining of I guess digital being figuring out how to connect digitally has really opened up a lot of opportunities for us. So it's been fun on my end too to get to participate in events like this.
And before you get going, I think our Vice President Sona was going to say a few words.
Oh yes, please. I don't want to cut anybody off.
No problem. Okay, I also wanted to welcome everyone. Thank you for joining us tonight for this very special event. My name is Sona Gevorkian, and as Meg mentioned, I am the Vice President of AWA+D. I wanted to introduce our speaker, who really doesn't need introductions. If you're an architect and you're on Instagram, you probably know Christine Williamson of Building Science Fight Club. And if you're not an architect or not on Instagram, you probably also know her. I contacted Christine on Instagram, and she was very gracious to accept this invitation to educate us on the building science. This is such an important but intimidating topic. Christine not only makes Instagram scrolling productive and educational for us, but also helps us grasp this overwhelming topic in a very easy and understandable way. When I talked to her, she shared that she wants to help architects to be confident in understanding the building science. She has developed classes to help us do that. Please check out her pages that I will paste in the chat. And Christine, thank you so much for joining us tonight and for sharing your knowledge.
Oh, thank you so much, Sona. This is it's really a pleasure to connect with other professionals in different parts of the country. It really is a pleasure. So I'm going to talk a little bit about why buildings leak, which seems super obvious, but it helps to take a more disciplined approach to that as I hope that we'll see together. But I wanted to, before getting into this, really say that this is, as I understand it, this event is a little bit more relaxed and social in nature. So there's obviously a very technical, and this is a presentation I have prepared in advance. This isn't off the cuff. So there's an element of formality to this part, but I'd really like to encourage and invite good actual conversation afterwards, or even throughout if you want to interrupt, but I can't see the chat. So someone else will have to interrupt me. If someone who can speak can interrupt me. But I'd like to encourage you and invite you to ask questions that go beyond the scope of this particular topic. I think that there's a lot of, in professional practice, there's a lot of kind of adjacent issues that we contend with all the time, like how much detail is appropriate to include in a drawing, for example, or a drawing set, all kinds of stuff. And just because it's not immediately related to this topic doesn't mean it's not worth talking about. And I'm really pleased to do that too. So please feel free to do that. And with that, I'll start talking about why buildings leak. So again, this seems super obvious. It's not like anybody stands with a bucket in hand under a hole in a roof during a rainstorm, wondering what's going on. But for architects who are not just designing something beautiful, but also running a business, it really does help to take a more intellectually disciplined approach to buildings and to design. So with that in mind, I want to start with the 3 approaches to water control in walls. So, and there are in fact 3. There's storage, WRB, and drainage. I'm doing this this is how informal this is. I'm doing this with a puppy in my lap. And so she's sort of squeaking her toy. She's teething. So anyway, if you see me squirming, I'm squirming for a good reason, for a very cute reason. And we're just gonna go with that. You can hear that, right? Anyway, she just learned to do that today. Okay, so 3 approaches to water management, water control in walls: storage, WRB, and drainage, and exclusion. And it helps to go into still more detail. The storage approach involves the wall absorbing water, redistributing that water, and then releasing it by drying. And this is how mass walls manage water. The mass wall gets wet. It has an enormous capacity to store and redistribute that water, and then it will dry in both directions. And this works really well because mass walls are built out of materials that aren't moisture sensitive. So there's nothing to become damaged as a result. These walls have a long history of performance, and indeed, many of the world's most beloved buildings manage water in exactly this way. The classic example of this kind of approach to water management is the solid masonry wall. And masonry walls can take a lot of forms. We apply stucco renders to them very commonly. And it's also very common for us to have the more modern composite walls with combinations of different kinds of stone and block. These types of walls are very durable and they're very heavy. They literally weigh a lot. And they also tend to cost a lot, in part because they are so heavy. Windows, doors, and service penetrations are sealed to the exterior. So mass walls, first category. Drained walls are the second approach to water management in walls. And these walls have a cladding that sheds water and a water control material and drainage space behind the cladding to protect the rest of the assembly. The building code calls the water control membrane a WRB, or a water resistive barrier. And we seal windows and service penetrations to that water control membrane. And the idea here is that we can build lightweight framed walls as opposed to those heavy solid masonry walls. And we can build our lightweight framed walls out of moisture sensitive materials like wood if we protect the moisture sensitive materials from excessive wetting by having a cladding that sheds water and some kind of membrane behind that cladding to protect the moisture sensitive parts behind it. This is an absolutely standard approach to water management in North America, and it's part of the reason why building is so inexpensive here. Framed construction out of lightweight, moisture sensitive materials is, it's really an extraordinary innovation. There are trade-offs to this approach. There are always trade-offs, but this is really a wonderfully clever innovation. The third approach to water management in walls is exclusion. So we call barrier walls or perfect barrier walls. And windows, doors, and service penetrations are sealed to that exterior surface, that exterior barrier. This is the least common approach to water management in walls, and it's the most tricky. Structural glazing work, the Apple Store, it's sort of iconic example of it. And a lot of insulated metal panels work this way as well. there is nothing wrong with this water management strategy, but its application is very narrow. So most of the time, it's really just not realistic to create a perfect barrier for water and still build the type of building we want to build out of the type of materials that we want to use. Many of the most popular building materials just don't lend themselves very well to perfectly blocking water and doing that throughout the entire service life of the building, which is really why this is such a narrow thing. Now, the trouble really comes when we mistake one of these water management strategies for another. And as we will see, we tend to not like the results very much when we treat a drained wall, for example, as though it were a mass wall or a perfect barrier wall. And it's important to point out that this discussion here, how we've started with these 3 water management types for walls, is a really significant difference in how a professional approaches water management in design and how lay people, including many of our clients, approach water management. Most of our clients, I bet, assume that there's only one approach to water management, to the extent that they think about it at all, and that approach is exclusion. So they don't understand how mass walls work, they don't understand how drained walls work, and that can make communication difficult. So we've got these 3 water management strategies for walls. What happens when our water management strategy fails? What does failure really actually mean? For water infiltration to be problematic, the wetting a wall experiences must exceed its capacity to store and redistribute water for long enough to damage the materials that compose it. This is super, super, super important, and it's so important that I'm going to repeat the sentence again, even though it's written right on the screen here for you. For water infiltration to be problematic, the wetting wall experiences must exceed its capacity to store and redistribute water for long enough to damage the materials that compose it. And what's kind of neat here is that this really does help us understand our 3 water management strategies a bit better. So mass walls work because of their ability to safely store lots and lots of and then dry out. Perfect barrier walls work by being perfect barriers, by not letting any water in the first place. But the middle strategy, WRB and drainage, is a little bit more tricky. And even otherwise smart and experienced professionals get this wrong a lot. A lot of people, architects, enclosure consultants even, think that all walls ought to be perfect barrier walls, and that we only add drainage and drying as a backup in the event of failure. So they think of drainage and drying as the equivalent of a lifeboat. They agree, of course, everybody agrees that lifeboats are important, but you only ever use it when something else has gone very, very wrong. And this is not true of walls. And it really reveals a fundamental misunderstanding of water management design. When we fill a bathtub up with water, take a bath, drain the tub, and then the next time we want to take a bath, we fill up the tub again. Nobody thinks there's anything wrong with that. The drain tub isn't a defect. It's how the system is designed to work. And that's the same case with drained wall. Drainage is a feature. It is not a defect. The issue now becomes one of capacity, right? So, and really that's what this sentence is reflecting. What is the rate of wetting for any given wall? And context really matters here. Are we in Chicago? Are we in San Diego? What is the wall's safe storage capacity? So how much water, how wet can it get? Safe and hold, how much water can it safely hold? And then what is the rate of drainage and drying? So as long as storage plus drainage and drying exceeds wetting, we're good. And but of course, how do we know that that's going to be the case for the wall that we're designing? And that's really the more complicated question for us. And to answer that, it helps to get still more specific about what constitutes a failure, what constitutes a leak. So a leak requires 4 things. It requires a source of water, a pathway for that water to travel from where it is to where we do not want it to be. It requires a driving force to push water along that pathway, and it requires something to be damaged as. And we need all 4 of these conditions to be satisfied for us to have a leak. And the reason this is so significant is because we usually spend all of our time and attention where? On that second requirement. We are obsessed with eliminating the potential pathways for water in our buildings. And that's fine. It's not a bad thing, but it is not the only strategy that's available to us in seeking to mitigate leaks. And it's often not even the most effective strategy. So with that in mind, let's go into detail about each of these 4 requirements because it'll help us contend with leaks and avoiding them much better. So what are the most common sources? Rain and groundwater, pretty typical. What are the most common pathways? Joints, transitions, penetrations, particularly those for windows, doors, and services like plumbing, penetrations, electrical conduits, that kind of stuff. But also fasteners, right? We have a lot of fasteners that hold the sheathing in place, fasteners that hold the water control layer in place if we're using a mechanically attached membrane, and fasteners that hold the cladding in place. So we've got lots of pathways, potential pathways. And what about common driving forces? We've got gravity, hydrostatic pressure, wind, capillarity, and surface tension. And we're going to talk a little bit more about these. Dealing with the driving forces is really the low-hanging fruit for us most of the time in water management. So if we can reduce the forces that actually push water into our buildings, we don't have to be perfect at source control or at sealing our pathways up. And again, we're going to talk about how to do exactly that, but let's finish going through our list here. What are the most common materials at risk of damage? Anything moisture sensitive, especially wood-based sheathings like plywood and OSB, trim, flooring, insulations, paper-faced gypsum. There's no shortage of moisture sensitive materials in our buildings. Now, sometimes we can replace some of those materials with non-moisture sensitive or less moisture sensitive alternatives, but oftentimes that's really not very realistic for us. So it's really these top 3 areas that are the most fruitful in devoting our resources to addressing. So let's look at some examples of some of these things. Common pathways, just some images of common pathways. If you're using a mechanically attached membrane like Tyvek, which is very uncommon in California, more often used tar paper or asphalt impregnated paper, felt paper. Those are stapled in place, and the staple provides a pathway to the interior. You've got sheathings that we have to attach the sheathings. Those are still more pathways. If you're using an water plus air control membrane like a zip sheathing, also sort of uncommon in California, but those are pathways too. There's a commercial version of the same thing, Georgia Pacific's dense element, where it's you just detail the seams, it's gypsum based, but anyway, you've got those pathways too. So we've got those types of fasteners. We also have fasteners that hold the cladding in place. So this is a wall, and you can see the brick ties on the wall. I think you can see my mouse here pointing at the brick ties. Those are on a commercial wall, but on residential walls we have brick ties too. If you're using brick, if you're using there's a bigger view of the brick tie. Any cladding, unless we're adhering it, which we occasionally do, but unless we're adhering, any cladding is going to have penetrations. We've got lots and lots of them. Oftentimes thousands. We have thousands. And it's not practical to seal a lot of these. Sidings, we blind nail them. Those don't get sealed. So we've got no shortage of pathways. Other forces, surface tension. So these are forces that take water from one place to another. And we're not going to talk about all of the ones on that list, just some of the less obvious ones. I'm not going to explain gravity. We have a pretty good handle on how that one works. But some of the less obvious ones like surface tension are kind of worth looking at. So surface tension describes the tendency of water to stick to a surface. And the most common architectural example of that is water tracking back horizontally along a soffit or some architectural detail rather than dripping down because of gravity. Capillary movement is the movement of water within the confined space of a porous material due to the attractive force of surface tension. So capillary action is actually, maybe surprisingly, a form of surface tension. And a practical example is when you dip a paper towel into a cup of water and you watch the water wick up through the paper towel. The same thing happens to all kinds of building materials, particularly cementitious building materials like brick, stucco, concrete, mortar. And capillary movement, if you're remembering from elementary school or high school, it's also the same force that brings water up to the leaves of trees through the roots and the trunk and the branches. And what's helpful about thinking about trees as an example of capillary movement of water is because, of course, we build with wood. And also because we intuitively know that trees can be very tall, which is a really powerful indication, just intuitive indication of the magnitude of capillary transfer. It really does indeed bring water in perhaps surprising ways through our building materials. But the real money for us is in understanding hydrostatic pressure. This is an extremely important mechanism, transport mechanism for liquid water. And you'll want to take your time here to understand this, but don't worry, stay with me. It only sounds complicated. So remember how capillary action is a form of surface tension. Well, hydrostatic pressure is really just a form, or it's a special kind of gravity. And hydrostatic pressure is the pressure that water exerts against a surface when it's held up against that surface. Classic example of that is a lake and a dam, and I'm showing the Hoover Dam here as an example. The dam holds water back, and the water in turn exerts a pressure against the dam. But the pressure on the dam isn't the same at every single spot on the dam. And in order to understand the pressure that the water exerts at any given point on the dam, we have an equation. And you will not need to run this equation, but it helps to actually look at the equation. Hydrostatic pressure, P, is equal to the density of the fluid, which is water, times the acceleration from gravity, G, times the height of the column. When we say column, all we really mean is how much water is above us expressed vertically. So if we look at this a little bit more carefully here, the fluid that we care about is water, right? So the density of water is always the same. So this number is going to be the same for us when we're dealing with hydrostatic pressure in buildings. And we're building here on Earth. So the acceleration from gravity is the same. So if hydrostatic pressure, P, is equal to the density of water times the acceleration due to gravity times the height, and the first two things are always the same, then hydrostatic pressure from water on Earth is entirely a function of this one, of height. So the height of the column. And in fact, that's exactly how we express hydrostatic pressure. We talk about inches of water, and this is why. This is where that comes from. It's the number of inches is the only variable that varies. So if we return to our dam here, the size of the lake bears no influence at all on the pressure against the dam. It's the depth of the lake that matters. So the bottom of the Hoover Dam needs to withstand enormous pressure. but the top of the dam, say 1 inch below the surface, experiences the same hydrostatic pressure as 1 inch of water exerts in my glass of water. It's exactly the same. And in fact, both the water in Lake Mead, 1 inch below the surface, and the water in my glass, 1 inch below the surface, exert exactly 1 inch of pressure on the concrete or the glass, respectively. So let's actually, now let's take that and let's apply it to a building. This is a standard residential wall with a brick veneer and a typical mechanically attached WRB behind it. And what I want to do is go through the four our 4 elements of a leak to see if we have a problem and what the potential remedies are, just as an example. So we want to identify sources, pathways, driving forces, and materials at risk of damage. So if we take a look at this standard residential wall, do we have a source of water? Yes. It's not in the photo, but rain, right? Can we do anything about that source? Absolutely. And we do it all the time in architecture. We have stuff like overhangs that reduces how much rain the water is ever deposited on the wall in the first place. We can reduce the height of the wall, perhaps by limiting ourselves to only 1 or 2 stories. So we reduce how much water the wall will see. Now, in certain kinds of construction, a lot of commercial construction, for example, where that's not, obviously some of these options are more or less realistic depending on other project constraints. But even in commercial construction, you can have a cornice at the top that really does have an effect on source control. What about pathways? So are there pathways for water to get from the exterior into the wall assembly itself and then onto the interior part of the building? Absolutely. We've got lots and lots of penetrations through this wall. Even if we set aside the windows and the service penetrations and think only about the field of the wall, we've got fasteners that hold the sheathing in place, which we can't see because they're behind the WRB, but we've got fasteners that hold that WRB in place. Here's a cap nail. Actually, I think I have a cap nail. I got a brick tie. I don't have a cap nail, but anyway, you've got mechanical penetrations there. This is a residential brick tie, the sort of corrugated kind. So yeah, these get fastened into the wall and this gets bed into the mortar there. But those are pathways, right? Those are pathways. But those are all behind the brick. Are there pathways for water to get from the front of the brick to behind the brick? And of course, here the answer is yes as well. It's almost shocking, actually, how easily water moves through a brick veneer. If you ever get the chance to do this on a job site at a mock-up, or maybe while something's in progress, you hose down a brick veneer and look at the other side. It's just to get a sense of the magnitude of water we're talking about. But water really does pass very easily through the pores and the capillaries, both of the brick itself and also the mortar. And so that's where surface tension and capillarity come into play, is that kind of inward drive. So we've got lots of pathways. Do we have driving forces? I guess I got ahead of myself a little bit. That pushes water along those pathways. Yes, we do. We have wind. We have capillary pressures to get water behind the brick. And then we have hydrostatic pressure. And remember, hydrostatic pressure is the pressure that water exerts against a surface when it's held up against that surface. Now, do we have that problem here? And the answer is yes, we do. Now, usually there is a gap between brick veneers and the sheathing and WRB behind it. And that's the case here too, right? We have about a 1 inch gap between the two, and that's very standard in residential construction. If that gap were completely clear, if it were actually empty, which is of course how it's always drawn on our drawings, we would not have a problem. We'd be totally fine. But it's not clear here. We've got mortar droppings filling that gap. And what do the mortar droppings do? Not only does the mortar itself facilitate additional capillary transfer through the mortar, but the mortar droppings also allow water to become what we call perched against the sheathing. And the more that water accumulates, greater the pressure driving that water to the interior. If we have an inch of accumulation, say right here, then we have what? An inch of pressure, which is a really big deal. And this is what causes leaks a lot, is an inability to drain. We allow water to build up, and now our water shedding materials have to become waterproofing. So we've got a source of water, we've got lots of pathways, we've got driving forces. Do we have anything at risk of being damaged? Yes, we do. We can't see the rest of the wall behind the WRB in this photo, but we can presume that there's plywood or OSB, there's fiberglass batt insulation in the cavity, and drywall on the interior, and all of these things are moisture sensitive. So the kind of question here, the natural question is this wall going to leak? And the answer is yes, it will. This is a real wall. It's in Louisiana, actually, in Baton Rouge. I took this photo. What is the easiest thing that we could have done with the least effort to address the problems in this wall? And that is, we could have kept that cavity behind the brick veneer clear of mortar droppings. So if that space were clear for drainage, it means we would be removing the hydrostatic pressure, and the space would also break up the capillary flow through the brick and the mortar. So if we were to deal with the driving forces, the pathways would become less important. And this is just really, I think, freeing for a lot of designers to understand that this tool is available to us. And I'm not telling you that you shouldn't seal the potential pathways for water in your assemblies. What I am telling you is that from a water management perspective, sealing the pathways is not the most effective strategy to pursue by itself. So what I'm telling you is really to think holistically about water management. And when we do not think holistically about water management, we tend to not like the results. This is what insufficient drainage looks like. This is a townhouse in Houston that's back. They had to resheathe, reclad, and re-insulate because the exterior walls were rotting. It was after about 5 years. And the OSB would just fall apart in my hands. It was worse under windows. This was not because the windows were poorly flashed or installed. It was because the water load is greater under windows, because 100% of the water that hits a window cascades down off the face of it. The window doesn't have any capacity to store and redistribute water, so the load under the window is higher. Single family home in New York with exactly the same problems. This is lack of drainage. This is not an installation defect. This is not a labor issue. And we see the same issues with commercial buildings. Now, obviously the physics is the same. Science doesn't care what we're using the building for, but for commercial buildings, the water load is often much higher. So we have less in the way of source control for commercial buildings because they're taller and they often don't have a lot of the popular design features that help facades manage water, like overhangs and porch roofs, inset windows. And this is something to keep in mind when you're designing a commercial building or a very large residential building or a modern building without a lot of those traditional details that help with water management on the. And this isn't to say that those designs are irresponsible. It's just that when we make design decisions that give us less in the way of source control, we want to make other decisions to compensate for that. For example, by improving, investing in better water management detailing, in maybe more rigorous oversight during construction, and more drainage. This building was in downtown Dallas, where it's 13 years old and they're having to resheathe it because the sheathing was already rotten. This is a zoomed in photo that shows you what's left of the old sheathing at the edge of the window there. And that tiny little corner of the old water control membrane is there. What's crazy about this particular building is that they went back with exactly the same poorly detailed assembly that caused the problem in the first place. This was a stucco building. And this problem is just constantly misdiagnosed. We blame these failures on poor workmanship. The reason goes, well, if the stucco didn't crack, the sheathing wouldn't rot. And that is not true. This is not poor workmanship. This is a design problem. We don't have enough drainage in these walls. We're not properly dealing with the driving forces. So, and we see this in big buildings too. This is very tall building, commercial building, and it was using, and not necessarily wood-based materials. So this is gypsum sheathing here. And the assembly is, this is a cement board with a stucco render applied on the other side of it, which you can't see. This is a building return. And then this is the tar paper here. And they had a fluid applied water and air control membrane behind that. The tar paper, the asphalt impregnated paper, number 15 felt, number 30 felt was used as the code required second layer, ostensibly to provide drainage behind the stucco. And it just wasn't enough drainage. We're getting through every fastener, we're getting water leaks from that. So let's look at that more carefully. What we really want is some kind of gap behind our cladding to relieve the driving forces that push water into our walls. And I'm going to show just an idealized stucco wall as an example, and we want to talk specifically about what that space does for us. So first, it provides drainage for liquid water that bypasses the cladding through larger cracks and penetrations that relieves hydrostatic pressure. It acts as a capillary break and a receptor for capillary water interrupting flow. And it provides a gap that facilitates hydric redistribution and moisture removal by air exchange. What's a more down-to-earth term for that? Drying. It gives us drying. So just a moment ago, I gave you that sentence to potentially memorize, or we repeated it twice. To store, for water infiltration to be problematic, the wetting a wall experiences must exceed its capacity to store and redistribute water for long enough to damage the materials that compose it. Well, the drying helps with that last part, the for long enough part. If we increase drying, we decrease risk. So we know we need a gap behind our cladding for drainage and drying. The next logical question is a much harder question, and that is, how much of a gap do we need? And in buildings that receive 20, or for climates that receive 20 inches of rain or more per year, and for buildings that are more than 2 stories, I recommend providing a space of about a 1/4 inch behind what we call reservoir claddings, which are claddings that hold a lot of water, like brick, stucco, and stone. Vinyl sidings and metal claddings are examples of non-reservoir claddings, just as a point of contrast for you. So 1/4 inch gap for tall buildings anywhere, or for buildings of any height in wet climates, which we arbitrarily define as 20 inches of rain or more per year, which is not a lot of Southern California. On more arid climates, I guess, less wet ones, a 3/16 inch gap works really nicely in lower exposure areas and for non-reservoir claddings, which is really pretty modest. That the space does not need to be that big, but it needs to be there. It needs to be present. So once you decide how much of a drainage gap you want to provide, you'll need to figure out how to physically do that, how to create that space. And the good news for us with this is that there are a lot of options. You can use drainage mats, furring strips, there's cladding clips, masonry anchors, textured building wraps. What I'm showing here is a drainage mat, the mesh kind of drainage mat. And you can see that it has a facer on one side of it. That's particularly helpful behind stucco claddings, because you don't want the stucco to, to clog up the mesh. This is another drainage mat. This one's made by Benjamin Opdyke, and it has no facer on it. And they make products with the facing and without the facing. And in the photo, it's being used behind a panel cladding, like a flat panel cladding. You need some way of offsetting the panel from the water control layer behind, and you could use a drainage mat for that purpose. And that's what that looks like. This is another one by Dorkin, which is a company I like a lot. Lots of Canadians there. Everybody likes Canadians. But this one is unique. It's got an integral fiberglass lath that's already attached, which is really cool if you're cladding a stucco. So there's not a separate like a separate metal lath. It's the drainage mat and the lath in one. This is what a drainage mat looks like on a building. This is a multi-family mid-rise project in Atlanta. And the drainage mat is the mesh kind, but that mesh is facing inward again so that the facing stops the mesh from being clogged with stucco. What's important to remember about this is that the drainage mat is just a spacer. So it should be entirely behind the cladding. It doesn't need to be integrated with windows or service penetrations. You can see here that the drainage mat just dies at the edge of the window. And the J termination that will terminate the stucco is in front of the drainage mat. We don't need to lack the drainage mat into the cladding terminations. Let the drainage mat be for drainage and the cladding be for cladding. There's no special detailing required. It's just a spacer. So this is what a different drainage mat looks like on a single family home. And again, that drainage mat just dies at the window there. It's just a spacer. The J termination for the stucco will come later. And really it's going to be installed as though the drainage mat weren't even there. This is the base of the wall of the same home I just showed you. And you can see, again, the drainage mat runs behind the weep screed for the stucco. And this is a little bit less intuitive because of the name that we give this. We call this the weep screed, but these little holes fill up with stucco and they don't actually really drain very well. So the drainage occurs behind it. This is really just a termination. This is an example showing exactly that. So here's our weep screed filled up with stucco. It's not going to drain. This here is we've got a drainage mat behind it, and this is a little cladding, a little piece of through wall flashing with a little kick out there. So you get your drainage in between these two things. It's all you basically don't even see it. But there is an outlet and it's open and clear. You can also just use furring strips. Classic wood strips run vertically to offset the cladding from the face of the water control membrane. This is a photo of sill seal run vertically to the same effect as a traditional wood furring strip. Sill seal is kind of neat. I like this approach a lot because it's really low cost. When compressed, it provides about a 3/16 inch gap. And what's cool is that sill seal's almost always already on the job. It comes in rolls, and this is the same material that gets installed under the bottom plate of your stud wall. It separates the framing from the concrete. And I mean, it's super inexpensive. So that you've probably seen this like lying around discarded on a job site. It's basically free, I've indicated, but you can run it vertically like this to give yourself just enough of an offset to give you some drainage and drying. Again, you can also use more traditional furring strips. Sometimes they come in plastic or other kinds of sort of mesh to allow you to run them vertically or horizontally instead of vertically, so that that can accommodate different fastening patterns for different types of cladding. They give you more freedom as a design. You also can pick a cladding that's naturally offset that provides a natural offset, whatever the cladding clip is. In commercial construction, it's pretty easy to do this really. The gap behind brick veneers in commercial construction is about 2 inches usually, and that's very reasonable to keep clear. I mean, you have to ask for it and you'll pay attention to it on site, but it's not that hard to maintain drainage consistent, a clear, consistent pathway for drainage with a 2-inch cavity. In residential construction, that gap is often only 1 inch, and that is hard to keep clear. So if the masonry cavity is only 1 inch, I'd recommend using just buying a drainage mat. Drainage mat, by the way, is about $1.50 a square foot. The hard part about drainage mat in California in particular is I've had a bear of a time actually getting subcontractors to install it. Stucco contractors themselves are like, I can recommend it as a consultant, the architect can draw it, the owner can want to pay for it, and the contractor can be on board. But getting a sub to agree to do something differently can be hard. So you get a little bit of the tail wagging the dog on this stuff, but you do the best you can. Another alternative is to use, also works very well in California, is to use textured building wraps. So sometimes you don't need that much of a space, and a lot of, if subs are not very inclined to installing some sort of spacer that they're not used to behind their cladding, you can use a textured building wrap as sort of a middle step. And those are just what they sound like. It's like, this one is made by Tyvek, and it's basically a crinkled version of their product, and the crinkling itself gives you just enough room for drainage and drawing. A lot of other companies make them. Benjamin Opdyke, who makes a drainage mat, also makes they sort of have like little plastic spacers on a traditional building paper that, again, give you just a bit of a gap for drainage and drawing. Tamlin, company out of Houston, has a similar product. So there's lots of low, and these are not very high alternates here. These are very easy things, comparatively speaking, to integrate into a job. Now, before finishing, I'm going to touch really briefly on this because I want to leave a generous amount of time for questions. But once we've got a space for drainage and drawing behind our cladding, we need to make sure that we actually connect that space with the exterior. So we want to make sure that water that does get behind our cladding, and we know it will, we want to make sure that that gets directed to the exterior in a way that we design, not someone else, or not like we don't want to leave that up to chance, because the water will find a way out or it'll find a way in. And we want to make sure that we do that in a way that is compatible with our design intent and our other goals for the project. So provide through wall flashings and weeps, allow the water that reaches the water control membrane to drain to the exterior. So provide some sort of connection for that, sort of an idealized version of that. The weeps that we provide at the bottom of a building allow water out, but it also allows air in. And ideally, we would also be providing an outlet at the top to actually get air exchange to enhance our drawing. And we essentially call this, what we want to do is we want to uncouple the cladding from the rest of the wall. And that's a really nice thing to do. This is what it looks like when we've got through wall flashing and a weep in the joint done nicely. And you notice that the weep is sitting right at the bottom of the through wall flashing. Here's what it looks like when it's not quite done right. It's elevated, which means we have to accumulate about 1/4 inch of water before it hits it's like this would be like setting your drain too high. This is not tragic, by the way, but it is good practice, and it's helpful to look at it when you're in the field. So there's better and worse ways of doing that, of providing through wall flashings and weeps. This is polyethylene. Or sometimes visqueen is used. It usually doesn't hold up very well during the construction process. This is a self-adhered membrane used as through wall flashing, and it's just sloppy. It's expensive. This is expensive and sloppy, and not super effective. But the worst through wall flashing is no through wall flashing at all. And this is sort of the joke, like the weep now or weep later. which is actually more clever than I gave it credit for. I thought that was very cheesy when I first heard it, but it makes sense, right? So either you decide weep now where the weep is going to go, or your wall decides for you. And this is ugly and it's gross, and you're getting discoloration of the sealant joint and all kinds of other stuff. But what's also worse is what we don't see. So where all the rest of the water is going, and it's in that wall. This was a really disgusting, this was a guy, by the way, he designed this house. He's a doctor, bright man, had his own very successful practice, and decided that he wanted this fancy modern house, and he was really smart, and he was smarter than everybody else, and he didn't want an architect. So he designed it himself, and his house is 3 years old, and it has lots and lots and lots of problems. So anyway, weep now or weep later, buddy. Okay, so where does this leave us? A leak requires a source of water, a pathway for that water to travel, a driving force pushing water along the pathway, and something for that water to damage. Mitigating the driving forces that push water into our buildings is much more effective and reliable than attempting to seal up all of the potential pathways. There is no commercially available water control membrane that is sufficiently self-sealing to overcome hydrostatic pressure. If you truly had a limited budget, you would be better off downgrading your water control membrane and buying drainage mat than you would be to spend money on a better water control membrane, a fluid applied or a self-adhered membrane. This is really, and that's sort of, there's some real beauty to that for us as designers, I think. This is, the more effective way of mitigating risk is a design issue. It's not a product issue, or this isn't something that you just buy. This is something that you design into your buildings, which I think is lovely for us. It's not a product thing. So making good decisions about water management, know what your building's water management strategy is. Is it storage? Is it perfect barrier? Is it drained in WRB, and detail accordingly? Specify the best water and air control membrane that you can afford, and make sure that it's confidently installed. Do the best you can at sealing the potential pathways, practice source control, and then make sure that you include drainage. This really is the lowest hanging fruit. If, really, in my forensic practice, the majority of the failures I see are exactly this. It's just insufficient drainage. It is as simple as that. There are, of course, more elaborate failures, stuff that you're sort of like the gotcha stuff where you're like, oh my gosh, how did who would have known? But that is a tiny minority of building failures. The vast majority of them just involve drainage. And if you include drainage in your projects, a generous amount of drainage, your entire building becomes more forgiving of other problems, of other potentially more serious problems. So your building can tolerate a penetration that hasn't been detailed properly, or a window detail that's not quite right, because you have drainage. Now, I'm not saying that's an excuse to be sloppy, but this covers a lot. This does a lot for us, and it makes our entire design a lot more forgiving, and forgiveness is a good thing. And that's it. So with that, we have a little bit of time before the sort of official conclusion, but I'm really happy to stay longer to talk about technical questions and just general practice questions as well. So open it up.
All right. Thank you so much. Normally we would clap, but right now we're all muted. Everybody's welcome to clap or unmute if they'd like.
I'm going to unshare the screen so that I can see more of you. I can only see some of you. Now I can see more. I've got the gallery.
All right. I'll just read some of these questions. We've got some good ones that have come in. One is, could you elaborate on inset windows and how it benefits water drainage?
It can. Sometimes it increases risk because an inset window can be more more complicated to detail. We've got more geometries at play. So that's potentially something that increases our risk. But having the window inset is a little bit like having an overhang. So you're limiting just a little bit less, so you have a little bit less water that window sees by being inset. So if a window is very inset, like let's say it's inset, a foot, that obviously has aesthetic implications too, but that window it's like being installed underneath a canopy or some sort of generous overhang. There's a lot less likelihood that window will leak, even if it's been poorly installed. But again, a lot of windows are only inset just a little bit, so the source reduction is only very moderate, and now they're more complicated because we've got to detail all these weird geometries. But it does reduce it is a form of source control just a little bit, and I think it matters a lot in especially older masonry buildings with inset windows.
Yeah, that makes sense. Okay, the next one is there a best practices way to provide continuous insulation behind something like cement plaster finish that provides this gap/drying?
There's actually a lot of options for us with this. And I love that you're asking that in California. 3 cheers for that. That is fantastic. So one way is this depends a lot on what you're actually, your option is going to depend, or your options, or the decision you make is going to depend on a lot of other project constraints, particularly aesthetic constraints. But if you use a drainable insulation like mineral wool, you can count on that by itself to provide the drainage you need. So,
oh, good.
Yeah.
Because
yeah.
that's what we have specified right now.
Oh, it's wonderful.
So I was like, I want to use this, and I was hoping that would be the right.
It is a great product. Now you still have to do other, be responsible in other ways, in the normal caveats. But yeah, that insulation that drains that way is really wonderful for exactly that reason. If you're using a rigid insulation that's not drainable, like extruded polystyrene or foil-faced polyisocyanurate, those are so smooth and flat that it's really nice to provide a little bit of drainage behind them. And my favorite way of doing that is to use a textured building wrap. And in my view, that's like one of the best ways of using textured building wraps, because they give us a tiny bit of space, but we don't use a drainage mat, because if we use a full drainage mat, we end up compromising the R value of the thermal performance, because you always want to prioritize water management over thermal control, but you still want thermal control. So we want just the minimum amount of drying possible. So a textured building wrap behind a extruded polystyrene or something is really fantastic. And I also usually like to provide, depending on what I've got, I'd like to provide a little bit of drainage in front of the insulation as well. Exterior insulation is difficult to contend with. There's a lot of design ways that makes the design a lot more complicated, especially at building returns, at the windows. It's hard. And as much as I think a lot of people are like, no, it's not hard. It's the right thing to do. And it is the right thing to do. I'm glad our industry is moving this way, but it is hard. I think people who sort of dismiss it as easy I don't think that's very helpful. It's sort of like gaslighting the rest of us who are like, yeah, but it's hard. Anyway, the other thing I wanted to mention with that is one of the products that I think is super helpful in California in particular that I'm not seeing right now is a product called Zip R. So it's made by Huber, who makes it's really a lot less common in California. So it's the green stuff you see a lot of times. And it's what they do is they take OSB and they coat the OSB with a fluid membrane in the factory. And so your framer installs the framing and the sheathing, and the framer then in the field details the seams. So they tape the seams of the sheathing, So you're only doing the seams and the framer does it. It's not a different trade, which is also unusual in California. So in California, usually it's the cladding installer who's responsible for water management behind the cladding. This is a separate trade that, like, the framer ends up doing the water management, which is kind of weird. But here's why this matters. They have a product, Huber makes a product called Zip R, and it's the same idea where you're just detailing the seams of the joints of the sheathing, but it's got insulation, rigid insulation already adhered to the back of the panel. And what that means is that you're getting credit for exterior insulation because the insulation is outboard of the structure, completely outboard of the studs, but it's behind the sheathing. And the reason that's significant is because all of your details are the same. You seal everything to that outer, like your window gets sealed, your window detail is exactly the same. All of the water management details are the same. So it's a really nice way of getting the performance of continuous exterior insulation without having to contend with all like detailing new cladding returns, because you've got to cover the depth of the insulation on the outside. It's a slick technique, I think, because it allows you to kind of make minimal changes to how a job is sequenced, how it's bid, all that other stuff gets to stay the same, and you still get to use exterior insulation. So it's a nice solution. But I think you'll see that a lot more in California in particular, because you guys are ahead of the curve energy wise, but you don't have the skill set in among the trades to contend with exterior insulation right now. It's just not done that much. Whereas in the North, you specify exterior insulation, everybody knows well, not everybody, but pretty much the trade base, they're not going to look at you like you have three heads. They know how to do this. You've already got standard details. It's nobody's first time. Whereas in California, it's like, sometimes you get houses built without sheathing at all. So, I mean, there's a different approach, I think, that it gets, it invites a different approach.
Yeah. Oh, okay, thank you. There's so much, like, we could talk about so many things here. These questions are great. We will get through as many as we can. How would one address the gap if the wall is sloped or a roof wraps down to the ground continuously?
It's harder. I mean, I'm not entirely sure I can quite picture exactly what you're talking about, but or what the questioner is talking about, but the gap matters. So you have to find some way of maintaining that gap, or you change and you have a different water management strategy, right? You can pick a mass wall or a perfect barrier wall, but of course there's trade-offs to that too, right? A lot of times it really is difficult to detail a perfect barrier wall to actually be perfect. But yeah, there's drainage mats that work behind sort of like, you have sort of shingle style roofs that are kind of walled as well. And that's actually, I think that's the first drainage mat was developed. It was called Cedar Breather. And it was the mesh product behind sort of these shingles. Now it's actually a great application on a roof as well, even pitched roofs. So the pitch works in your favor, but it's, or a vertical wall works in your favor too. But drainage, in a lot of ways, if you've got something that isn't vertical, the more horizontal something gets, the more important drainage becomes, because you're dealing with more hydrostatic pressure, really. I hope that helps. I don't know. It's a little hard to know exactly.
He's nodding. I think so.
Okay.
He's good. Okay, good. All right. Could you address, I love this one. Could you address waterproofing a planter that shares a wall with a building?
Don't do that. So a lot of times we want planters to be close to our buildings, and that's normal and aesthetically very pleasing and great. I mean, maybe do it, I don't know. The problem with planters is, so I don't like doing that, but I don't always get to win in these negotiations. What makes that really difficult is planters are typically irrigated. We put things in planters that require water. And typically the best way of dealing with, you see this a lot on plaza decks, right? So we'll have a deck or an amenity deck for a commercial building, and we'll want that to be a nice exterior space, but we've got parking or we've got something underneath it. And the best way to reduce risk in that setting is to make the waterproofing completely continuous underneath all of the overburden, planters, curbs, architectural features, whatever else is up there. The waterproofing goes down first, and it's completely continuous underneath all of the structure. And then everything that gets built on top of that, we're already dried in. So ideally what you'd do is you'd have your waterproofing underneath your planter and integrated with the wall before the planter's even there. So you're waterproofed already. Then your planter goes in, and you may elect to also waterproof the inside of the planter, because it kind of takes the load, it reduces the load on your primary waterproofing membrane. But that's usually the approach I recommend. Most of the times, so failures on plaza decks and with planters is a really big deal. It happens a lot. It's probably one of the, if you're doing commercial buildings, really anybody doing commercial buildings, one of the highest risk, I guess maybe top 3 highest risk things that you do from a water management perspective are plaza decks, because they're so complicated. You've got just so much stuff going on. And if you have a problem, it's hard to find where the leak is, because you've got heavy, expensive to move stuff on top. So, and when we have failures, what's sort of even worse about this is that they're usually they're not installation failures or product defects. The failure is like 99 times out of 100 because of a gap in coverage of the membrane. Like a waterproofing membrane isn't going to waterproof where it's not applied, obviously. And when you've got a complicated architectural design on an amenity deck with planters and curves and all kinds of stuff, and patterns in the top, whatever the paving or the topping is, that stuff, like you get interruptions in, like, and these are big areas a lot of times. So your waterproofer will do some work over here and some work over there, and some of the planters are partially installed here and partially installed there, and there's a lot of different trades. So what happens is something gets missed and you don't even know it, and that doesn't get covered by, first of all, it's hard to find, and it doesn't get covered by warranties, because it's not a failure that's warrantable. It just sucks. Now it is your contractor's fault, but everybody suffers. The owner suffers, and you will suffer as a designer in this. Anytime it's painful and you argue about this and it's awful. But the best way to avoid that is to make the waterproofing continuous before the planter is in place. Takes a little creativity to do that, and practically speaking, it takes some discussion with the contractor on how they sequence that job, but that's a line in the sand that I will draw a lot of times for stuff, is that ends up being a sort of not optional discussion. Now, if you're already down the line with this and something's already designed and it's in progress, and you have to do the best with what you've got. But if I'm involved in a project early enough to have this conversation, that question is the top of my list.
Oh, okay, great. Thank you. In a more humid client, let's see, I've got one more. What would be the reason for leaks on top of windows? The top of windows.
At the top of windows?
Yeah.
I mean, I don't know exactly what you mean by that. I guess a lot of times windows aren't sealed well to whatever the substrate is. Oh, we get leaks, actually, that's okay. So we get a lot of leaks at the head of windows because people kind of misunderstand what the control layers are there for. And this is like, there's some nefarious activity, I believe, by materials manufacturers in this regard. So what do I mean by that? Our water control layer, I call it a water control layer, not a waterproofing membrane, because it's there to control water. We're managing water in our buildings. We're not blocking it entirely. And the sort of original water control layer, we actually didn't use it for water control. We used it for air control at first, is tar paper, like number 30 paper, felt paper. And we used to use this before we even had sheathing. So we'd span this across our studs, and it was a draft stop. Our buildings were extremely uncomfortable back in the day. And so we'd hang this heavy paper. It was because it used to really be, it got its name because like asphalt impregnated paper actually weighed 30 pounds per 100 square feet or 15 pounds per 100 square feet. That's not true anymore. They're much more dimensionally stable and they're not quite so heavy. But we used to hang this stuff, and then we'd have the cladding, and it stopped air from going through. The more modern incarnation of this, we use to control water in our buildings. We reduce how wet things get. But if we're using something that's mechanically attached, like Tyvek or tar paper or Typar or whatever it is, there's lots of these materials. If we're mechanically attaching it, so we're fastening it to the building, these materials are not fully bonded to the sheathing, right? They're just fastened at the fastener points. They're hanging there. And what that means is that air gets behind them, and a little bit of water gets behind them too. So we get water on our sheathing behind our water control layer. Now, we don't get that much water behind it. We just get a little bit of water. And in the field of the wall, it doesn't matter. Like, we get so little water, it's really no big deal. But at a window, what we find is we have to do this sort of the cut in the membrane, and we have to seal the window. We temporarily tack the tar paper up, and you seal the head of the window directly to the sheathing. You don't seal it to the water control layer, you seal it to the sheathing behind the water control layer. Why? Because a small amount of water gets behind the water control membrane, and it's enough to make a window leak. It's not enough to make a wall leak. And this goes back to the what are we really in the business of doing? Like, we're for us to have a problem with a leak, we have to exceed the wall's capacity to store and redistribute water for long enough to be a problem. Well, in the field of a wall, we actually do have most of our walls, even though they're made out of moisture sensitive materials, they can tolerate a little bit of wetting. At a window, it'll actually get to, we've got a pathway right to the interior, and it'll get to your drywall, and maybe it'll dry out, but your occupants will complain probably, and you'll have paint problems or something like that. So that's really common at the head of windows when we sort of mistake. Manufacturers of these mechanically attached membranes advertise their products as being like completely impervious in practice, and they're not. And that in turn leads to some confusion. And so intuitively they're like, well, why can't I seal my window to the head of my water control layer? That's what it's there for. It's there to control water. What's the problem? Well, that's not quite the full picture. So that's a very common thing. It's a common way of getting leaks.
There's a similar question, maybe it's part of the answer. How do you deal with hydrostatic pressure at the top of a large window? But I guess in a way it could be any window.
Or anything, yes, yeah. I mean, you provide, so what we want is we need to provide, if we've got a drained, so this is different than if we have a mass wall or a barrier wall, we seal our window to the adjacent surface, and everything is like everything's in plane, right? Like the exterior face of our barrier or the exterior face of our masonry is our water control, and so is the exterior face of the window. It's easy. Like, our jobs are a lot harder in North America than they are in Europe than our counter. I mean, there's probably other hard things. I shouldn't say that. I don't know. I don't know a lot about actual boots on the ground architectural practice in Europe, but that philosophy is it's so much more intuitive. And when I work with European materials manufacturers in the US, they are like mystified by the questions that architects ask them. They're like, what do you mean, how do you detail your window to my window to your cladding? Like, just seal it. Well, if you've got a drained wall, we can't do the same thing, right? If you've got a veneer, that the veneer's job is to shed water, not to block it. So we have water behind it. So if you've got a window system and you just seal it to the brick cladding or the, I mean, I guess it's got a brick ledge on it. So if you just seal it to your metal panel cladding or your panel siding or whatever, you're going to get a leak because you need to provide a what we call through wall flashing to direct water that gets behind our cladding out. And that is difficult to detail, and it has a lot of aesthetic implications to it. I think sort of one of the things that's kind of misleading maybe conceptually for us is we think that it's really hard to detail, like building science is hard building science makes windows hard to detail. That's not really true. It's connect the water control layer at the wall and to the water control layer at the window with a sealant joint and let it out. What makes this hard is that aesthetically that's hard to achieve. Physically, like structurally, that's hard to achieve. So how do we support our physically support the cladding and cover everything we want to cover and provide drainage? That's the part that's hard. And I mean, but that's why we get paid so much money, right?
There's I'm sure a universal chuckle in there. Yeah, that's great. Okay, we have, this is a big one. In a more humid climate with a higher wet bulb temperatures, are there water management practices for the interiors of buildings?
I mean, yeah, there are. But it's not, that's not as hard as it, I mean, it depends on what we're talking about. But yeah, so there's two ways that what we want to do if we're looking at a building from the perspective of a building scientist, and this is one of the hats that architects need to wear, is we consider a building an environmental separator. So what we want to do is create a particular set of conditions on the interior that may differ substantially from the conditions on outside. And we have two ways that we do that. The first thing we do is we physically enclose the space. So we want to physically separate the inside space from the outside space. And we do that with our control layers, and that's sort of intuitive to us as designers. But once we've done that, we now need to condition that space. And that is where mechanical system design comes into play. There's a lot of romanticism about like natural ventilation and that kind of stuff. And that can take the edge off of things, especially in California. But actually not for the most part, there is no natural way of removing humidity from an environment. It 100% of the time requires energy. And that means mechanically conditioning the space. So you can move air passively, and that can make people feel more comfortable. But if you are in a humid environment, there's no way of actually reducing the humidity without an input of energy. And so you've got those two. The enclosure design doesn't help you with that. So the design decisions you make about the layers that separate the inside from the outside don't actually help you condition the space. So most of the time we deal with those interior environments where we have to deal with the mechanical system design differently to deal with higher loads. So air that we bring in for breathing and for ventilation is humid, and it often makes sense to precondition air before we have it enter our space. We have a similar issue in very cold climates where the air that we bring in for breathing is very, very, very cold. So if we're relying on bringing in this air for safety and health and indoor quality, it's our responsibility to heat it, to precondition it, because if we don't do that, I've worked on some projects in the Canadian Arctic actually, where the design did not involve preconditioning that air. And so you'd get how this was in a lot of government housing actually. And so you had a lot of people living in very close quarters. So you had multiple families living in a single family unit, and it was very cold. So they disconnected. They didn't want interior air coming in, so they covered those vents. And without bringing exterior air in, the humidity generated by people and extra people on top of that from breathing, cooking, cleaning, whatever, created a bunch of mold problems. So, which is a design issue. I don't blame the occupants for being in Nunavut and not wanting to have like a lot of influx of very cold air. Anyway, so we have these issues in different kind of climates, but as we get better at separating these spaces, we can fine tune how we condition it quite a bit better than we used to. And we can do so more efficiently as well, which is one of the great things about getting better about detailing our buildings, is that it allows us to condition the air more easily and often more efficiently. So that's how we do. I hope that answers the question.
Okay. Yes, she's nodding. Okay, good. All right. So we've got time for one more. We really appreciate your time. We're almost.
Of course, it's fun. I'm drinking my wine, hanging out. This is great.
Party. All right. I love this question because I had the same one. Magdalena asks, the weep screed detail showed the drainage mat installed behind it. Generally, we would put a building wrap, building paper, atop the weep screed.
Yes.
Is there a termination strip for the drainage mat at the bottom of a stucco wall?
No, you don't have to terminate it. A lot of times you can if you want to. I kind of prefer having something there. So you could have a little, just like you would for another type of flashing, you could have like a metal kind of through wall flashing with a drip. So L-shaped with a little drip, and you could lap the building paper and drainage mat over that. And then your weep screed goes on top, and you don't care that the weep screed doesn't actually weep. Just make sure that nobody seals it along the bottom with a sealant joint. You want that to come out. But let's suppose you didn't do that. Let's suppose you just had the drainage mat and you left it there, and you put your weep screed, then you put the weep screed down. It wouldn't really be a big deal. So you'd get some water kind of dribbling down. I mean, it would dribble down. So you have, depending on what's underneath it, maybe you've got staining as an issue, especially if you're transitioning from one type of cladding to another cladding. But if it's at the base of the wall, you don't really have to do anything there. And we're not talking about a lot of water here, but especially behind stucco, stucco is actually very good at blocking most of the water from getting behind it. The problem is hydrostatic pressure. Stucco is so close to the sheathing and the water control membrane that even a little bit of water becomes a problem. And just a tiny bit of drainage really helps us. Back in the day, it was, so the whole idea, we used to use, I alluded to this earlier, we used to use very heavy asphalt impregnated papers, and they had a very high rag content in them. And we would use this behind stucco successfully. And the stucco would go on wet to one layer of felt paper. And as it was applied, the felt paper got wet and it would swell, it would expand. And as the stucco cured, the felt paper would debond from the stucco, and it would create a tiny little gap for drainage. And when we kind of reformulated these asphalt impregnated papers, we made them better. They're more dimensionally stable, and they don't swell up like this the same way that the old school ones did. So they remain bonded to the stucco, so we don't have that same drainage. Now, we knew that this was going to happen. So in around like 2000, the building code specified, okay, well, you have to now have 2 layers of building paper behind stucco. That's where that came from. The 2 layers was not because we don't trust the first layer. It was that the second layer was sacrificial. all it was a bond break, and the intent was to give us a little bit of space for drainage and drawing to mimic what the old papers used to do. And what we find is that works in a lot of scenarios. It just doesn't work in all of the scenarios. And so we're finding now that we have these huge problems with drainage and drawing in a lot of climates, because the code just isn't at pace, hasn't kept pace with the requirements of wetter climates and taller buildings. So it's not, so the code was already moving in the right direction. It just didn't capture enough of the cases. And now we know with experience that there are a lot of cases where we need more than just that second layer of building paper provides. So that's where that came from. But it's only a little bit of water. It's really not that much water.
Yeah.
So you're not going to get, even though we've got a drainage mat and it's relatively robust, this isn't like, you're not expecting an enormous amount of water there. But it is a helpful tool to have in the tool belt.
Oh, that's amazing. Thank you. Yeah. I didn't realize that about the 2 layers. That's so
yeah,
cool.
It's kind of cool to know where it comes from, because a lot of times people are like why, what is that for? Why don't I have to have 2 layers behind other stuff? Are we just assuming these stucco guys are just really bad at their jobs and everybody else is fine at it? No, it's the drainage.
It's the drainage. Okay. We didn't talk about this prior or just right before, but do you want to mention, now that we're wrapping up, do you want to mention emailing you for a drawing? You had a class.
Oh, I don't know how you want to handle this. Why don't you guys just handle it? I'll set you up.
Okay.
Oh, hi, Christine. There's someone else. Anyway, hi. There's a yeah, you guys can handle however, you set the rules. I don't know, make it like a gladiator style challenge, whatever you want to do, or just a drawing, just a lottery system, whatever you want.
I think we can do a lottery system really easily, but I think what we would like is volunteers. So if you are interested in, Christine, maybe you need to tell us what people would be winning, but we were going to do a drawing for something that Christine has offered to our attendees, which, now there's only 23 of us, so
yeah, you miss it. You're right.
Please let us know what it would be for, and people can put their email address in the chat. We'll save that. We'll do a random drawing. There's an app for that, and we'll do a random drawing of your names and provide that name to Christine.
So good. Yeah, it's good. It's so I offer and this is good. Take this class anyway. I don't want to be too self-promoting, but I genuinely think it's very, very helpful. I have a class in which I teach building science to practicing professionals, architects and architects in training. If you're somebody else in the building industry, it certainly would benefit, like a contractor or something else too. But I really wanted a comprehensive resource specifically for our corner of the industry and our community, because the decision-making process is different for architects when we're dealing with risk. And, the physics isn't different, but the way we parse risk and our role in projects is different. And so I wanted something just for us. And also, people aren't really talking to architects a lot about this stuff. There's not a lot of good resources, I don't think, for getting a comprehensive sense of dealing with risk and performance in buildings. So I came up with a class. It's in total, it's like 11 hours. You definitely don't take it in one sitting. I mean, you can if you want, but you take it however you want. Your access to it, it's on demand. So it's video lectures with sort of like a PowerPoint stuff, a handout, but you can download that and print them, whatever. Your access to it never expires. It's I wanted it to be comprehensive and a reference resource so that you can visit multiple times during your career over time as you take on a new project and some concept becomes relevant in a new way. You can revisit it. So it's an ongoing thing, but it's a comprehensive class on risk management, really. So we talk about the fundamentals And then there's a section on walls, roofs, foundation systems, and windows. And again, the whole thing is about 10 hours, but it covers this in a comprehensive way in 10 hours. It doesn't mean that you will never have anything else to worry about in your projects, but I'm pretty confident that you give me 10 hours and you'll feel a lot better about a lot of this stuff, whatever your sort of particular professional practice demands. It is pretty comprehensive, and the idea is really to get a better handle on this so that architects can be more creative and more confident in their daily professional practice. The more you know the technical fundamentals, the better you can design. You can focus on the stuff that most of us, apart from me, this didn't start out our careers wanting to worry about this stuff. But if you figure this stuff out, if you get that foundation, you get to spend a lot less time actually worrying about it and doing the fun parts. So that's the idea. And to take on the drawing, the random stuff, you can take this class for free. It'll be fun, I hope. Or just follow me on Instagram and you can get little bite-sized learning for fun and for free. And I hope that you guys do that and participate and ask questions and offer your own experience for that as well.
Yeah, thank you. So please put your email address in the chat before you leave if you are interested in entering the drawing. Otherwise, I think we should give Christine a round of applause. That was a riveting hour and a half of
amazing
waterproofing and detailing, and it was great.
Oh, thank you. I'm so glad. It's so nice to see you. I hope we can do this. I really do work in California a lot, and I'm like itching to get back there. I miss California. It has to be. San Antonio is my favorite city in the US. I really love San Antonio, but California is my favorite state. It is. You guys are in a heavenly place. Absolutely.
Got it pretty good. Yeah. Well, thank you so much. I see email addresses are coming in. Thank goodness. I'm sure there's a lot of competition, but